My name is Eric Glenn, and I am the Program Manager for Safety. We appreciate you joining the webinar on evaluation of narrow automated vehicle exclusive reversible lane on a exit SmartWay freeway. You all have come into the meeting muted, and we would appreciate it if you stayed muted until the Q&A session. If you have any questions during the webinar, please type them into the chat box and they will be addressed at the end. We will have captions on for your convenience as well. At this time, I would like to introduce the presenters. Dr. Sahar Machini is an Associate Director of the Safety UTC and Associate Professor of San Diego State University, Department of Civil Construction and Environmental Engineering. Sahar holds a Master's of Science in Transportation Engineering from Sharif University of Technology and a Doctor of Philosophy in Civil Engineering from Virginia Tech. Go Hokies. Before joining San Diego State University, she worked as a research associate at Center for Infrastructure-Based Safety Systems at the Virginia Tech Transportation Institute. She has expertise in traffic safety, driver behavior modeling, evacuation modeling, and infrastructure-based safety systems. I'd also like to introduce Alidad Ahmadi. He is a transportation engineer planner with nearly 6 years of industry and academic research experience in conducting transportation studies with a focus on safety, big data analysis, traffic simulation, vehicle miles traveled analysis, safe route to school programs, and parking studies. Alidad is best known for his visionary perspective, communication skills, and technical knowledge of working with various transportation data. Alidad earned his master's degree in civil engineering, transportation from the San Diego State University in 2017. He currently works and resides in the city of San Diego, California. Now that the introductions are complete, I will turn it over to the presenters.
Thank you, Eric. Let me start sharing my screen. Okay, are you able to see the screen?
Yes.
Okay. Okay, hello everyone. My name is Sahar. I'm an associate professor at San Diego State University and an associate director of safety UTC. I'll be presenting our work on evaluation of an automated vehicle dedicated lane on a freeway. Before I get started, I would like to acknowledge our partners' effort. This project was a partnership between SDSU Star Lab and LLG engineers with valuable feedback from our project champions at Caltrans District 11. I'll start with a little bit of introduction. Automated vehicles are emerging technology and autonomous driving is fast becoming a reality. However, complete transition to AV transportation takes time. A full infrastructure adaptation is not going to happen in a day, especially given that transportation system will be serving both AVs and human-driven vehicles for a while. So a mix of AV and human-driven infrastructure is a viable solution to enable a smoother transition to an all-AV world. With that, the question is, what are the implications of infrastructure adaptation to AV technology? Human-driven vehicles depend on driver capabilities and behavioral characteristics. AVs depend on several sensors to recognize surrounding environment and navigate. AV navigational capabilities could allow for infrastructure standard adjustments such as fewer number of lanes, fewer signage, and narrower lanes. Given the difference between the operation of AVs and human-driven vehicles and reliance of AVs on sensors as opposed to human capabilities, can we provide narrower roadways with more efficient right-of-ways, assuming AVs are more precise in lateral and longitudinal lane keeping behavior? what are safety and operational implications of these narrow lanes? These are the questions that we were trying to answer in this project. In addition to gathering general information on AV exclusive lanes, we considered the study site for an envisioned narrow AV lane suggested by Caltrans District 11. The project focuses on I-15 express lanes and evaluates safety and operational aspects of a 9-foot AV exclusive lane on I-15 freeway in San Diego. Here is the configuration of the envisioned AV narrow lane. The I-15 express lanes between State Route 163 and Via Ranch Parkway currently provide 4 HOV and 12-lane fast track lanes, with the lane configurations shown to the left, depending on peak direction and position of the movable barrier that separates the northbound and southbound traffic. There could be 2 northbound and 2 southbound, or 1 northbound and 3 southbound, and 3 northbound and 1 southbound. As shown to the right, in the available width between the fixed concrete barriers that separate the express lane from the regular lanes, it would be possible to add a narrow reversible lane to be used only by AVs. This reversible AV lane for travel in the peak traffic direction would be 9 foot wide and located next to the movable barrier. Here is the project's evaluation framework. We looked through AV manuals. We conducted a literature review first from literature review of all the AV systems. We looked through AV manuals and websites of 15 AV manufacturers. Next, we collected information from experts, from academia, transportation officials, and manufacturers. We also looked at NHTSA's consumer complaint database to understand issues related to lateral vehicle control technology. Then we focused on I-15 specifically. We extracted crash data and looked at history of different crash types and potential causes that could be partially attributed to AV system. The final task of the project was the microsimulation of I-15 that the next speaker will talk about it in details. For any of the other tasks that I briefly mentioned here, if you are interested to learn more, I encourage you to check out our full report on the safety website. But before I hand over to our next speaker, Ali, I would like to quickly touch on some of the general recommendations that we came up with from all the tasks of the project that were non-specific to I-15. First, a standardization of lane markings, signage, mapping of roads, speed limit, and geometries of AV operations on exclusive lanes are recommended across the nation, while still accounting for non-AV compatibility. Highly reflective, clearly visible, and distinct lane markings and signage are required for proper AV sensor operation. White lane markings surrounded by black paint could be effective. Signage such as keep lane assist on are recommended for all levels of automation, especially for lower levels. Same direction physical barriers between AV exclusive and adjacent lanes are recommended to prevent crashes. Also, barriers with active sensors may aid in lateral control of AVs by providing clear physical signals continuously measured by AV sensors. Lane friction could be used to determine if barriers are warranted. Lane friction is defined as the difference in average speeds of AV exclusive lane and adjacent lane. Depending on traffic condition and market penetration rate, restrictions should be placed to designate the lane as AV exclusive, shared with HOVs, or open to all traffic. There are expert recommendations suggesting that an MPR of 10 to 30% may be sufficient to make AV exclusive lanes viable, and that an MPR over 50 may warrant the commissioning of AV exclusive lanes. AV application limitations should be taken into consideration. For example, some AV lateral control systems, such as lane departure warning systems, are effective above certain speed, are operational for certain speed range, and do not perform well, for example, in sharp turns, during low visibility, or in foul weather conditions. Early education and training at the driver's license level, as well as extensive public outreach via internet, social media, and other campaigns are recommended to explain how the lanes should be used or not used by AV and non-AV drivers. Simulation modeling with real-world traffic data specific to the candidate site could be significantly helpful in making informed decisions on feasibility, limitations, and specification of the AV exclusive lane. Nighttime restrictions should be considered as vision-based sensor systems are vulnerable to low light conditions. Infrastructure non-idealities such as pothole, non-uniform lane markings, etc. should be minimized, as AVs are vulnerable to these non-idealities. Widening the lanes around curve is recommended, especially for a narrow AV exclusive lane, as generally AVs are susceptible to turning error. Operation of heavy AVs is challenging, especially for a narrow AV exclusive lane. So specific restrictions for heavy AVs should be developed. To support safe operation of AVs, roadside units that facilitate vehicle to infrastructure communications can be implemented to provide real-time critical traffic information to AVs. The access points to the AV exclusive lane need to be carefully designed and monitored to prevent unsafe lane changes, as well as manage traffic flow distribution on all freeway lanes. That was, I think, my last slide. Thank you so much. I'll be happy to answer questions after our next part of the presentation by Ali. So Ali, you could start presenting your work, and I'm gonna mute myself for now.
All right, thank you, Sahar. So I'll talk about the microsimulation part of our study. So here we're just going to do a brief introduction of the microsimulation. Based on a definition from the FHWA, microsimulation is modeling of individual vehicle movements on a second or sub-second basis for the purpose of assessing the traffic performance of highway and street systems, transit systems, and also pedestrian. So there are several steps that go into developing a microsimulation. The first step is the data collection and preparation. For our case, it included collecting the lane configurations, collecting volumes, and some local parameters like that. And the second step is developing the base model, which is basically putting together all the information that you have in the software. The third step is error checking. For our case, the error checking mostly involves looking at the alignment of the roads are fine, things like vehicle disappearing doesn't happen, the express lane is, the transition lanes are aligned right and connected right to the network, and all that sort of checking that you usually do with a simulation. The fourth step of the simulation is a calibration process where we run the simulation for several times until we have a network and a simulation that fully represents our conditions that are currently on the road. And the last step, which is optional, which we had for this, was to modify the freeway system that we had, the simulation network that we have, to identify the changes in the performance and the metrics that we're looking at in this study. Next slide, please. So in our simulation study, we have 3 scenarios that we are looking at. The first scenario, which we call the existing scenario, is the baseline scenario with the existing network and the existing volumes that are on the roadway. The second scenario that we looked at, which is called AV, is using the same volumes, but with the adoption of some percentage of the AV vehicles on the road. And the third scenario, which is the ultimum scenario, which we call AVL, is existing volumes with the proposed AV exclusive lane and the adoption of the AV vehicles on the network. Next, please. So the simulation network that we have put together here was conducted in the Transmodeler SE edition. At the time, we had access to version 5, which was the latest one. The simulation network is a 5-mile long part of the I-15 corridor, bounded by State Route 56 on the north and the State Route 163 on the south side. And there are 4 main interchanges in between these two boundaries, which is basically, if you're familiar with San Diego, this is one of the busy sections of the freeway during the commute hours. Next slide, please. So there are several physical features that need to be included in the simulation network. So some of the features that we have pointed out here that we have included in the network is the merge and diverge connectors, which are basically when you're on the main line of the freeway and you want to transition to the express lane, you use the merge and diverge connectors. There is an expressway direct access ramp located south of the Mira Mesa Boulevard, which pointed out as DAR in the picture. We have included that in the simulation network, and also the lane configuration that we have used for the simulation is the I-15 during the AM peak hours. So as Sahar mentioned, the I-15 has 2 configurations for separately for AM and PM commute hours. And here we have modeled it for the AM commute hour, which is basically 3 lines going southbound and 1 line going northbound. Next slide. So the existing volumes that we used for this simulation exercise was received from Caltrans, and the data represents a typical day, a typical weekday on the month of October of 2019. And the data collection was conducted for the AM peak hour, which is 7 to 9 AM. Next one, please. So there are several assumptions that we have included in the simulation. So the first assumption is a road classification. We have gathered some of this information from Caltrans and some of it from the standard guidelines. Some of these assumptions are the saturation flow rates, the speed limits on the freeway, the free flow speed, and the speed distributions on the express lane. Another assumption was made is that the heavy vehicles were not modeled in the simulation, and the reason is that it was assumed that the heavy vehicles are probably not allowed to use the express lane in the future. And all of the non-AV vehicles in the simulation model were evaluated based on the modified general motor car following model. And all the autonomous vehicles were evaluated using the constant time gap car following model. More details about those models also could be found in the instruction files of the Transmodeler software that we use. And at the end, the AV that we have adopted in the simulation was adopted through 3 market penetration rates for MPRs, which is 15% AVs on the road, 30% AVs, and then 45% AVs on the road. Next one. And for those of you that are interested to know a little bit more about the simulation, so the way that we have implemented the AV lane on the network was by designating an exclusive AV lane on the software by kind of defining a prohibition rule for the AV lanes to use certain lanes. So as you can see on the right picture, all the AV lanes were designated to use lane 1, which is a far left lane on the southbound direction, and lane 2 and lane 3 were specifically designated for non-AV vehicles. So the only way an AV vehicle could get into L2 and L3, or lane 2 and lane 3, is if they're exiting the express lane, or if they're entering the express lane, then they would cross over those 2 lanes to get to the AV lane. And that's kind of the trick that we use in the simulation network to simulate this, like a new proposed conditions. Next one. So the validation of our simulation included 60 minutes run of the simulation with the existing volumes and existing network, which also included a 50-minute warm-up time at the beginning of each simulation. We had several sensors along the road that collected the data, and then we compared those data to the field data that we have, the outputs from the simulation versus the numbers that we got from Caltrans. We use a method called the GH method, which is basically comparing those 2 values through some formulas, and then the low GH value, which is recommended to be less than 5, is considered a well-calibrated model in a simulation. So on the right side, you see that we have the scenario starting from, for the southbound direction, starting from north. We feed the simulation network with the volumes, and then as they go south, we record the data on multiple locations, and we run the simulation several times. We get the GH values until we get to a reasonable one, which indicates that we have a reasonably calibrated model to use. Next one, please. So here is a summary of the calibration that we made. So as you can see on the table, the last 3 columns, there's a delta volume, which is delta between the field volumes and simulation volumes, delta average speed, which is speeds on the field versus speeds in the simulation, and at the end, the GH value that was calculated. And as you can see, on both northbound and southbound direction that we run the model, we got very reasonable numbers. The volumes were as close as 2% to the actual volumes from the field, and speeds were as close as 5% to actual volumes on the field. And same for the GH value that we calculated. So all of the GHs that we calculated were well below the 5.0 threshold. Next slide, please. So the microsimulation results at the end were reported and reviewed under 4 following selected metrics, which is the traffic flows on multiple locations on the network, the average density, the average speed, and at the end, the speed differential between the lanes. So the speed differential between the lanes in our study was defined as the difference between the speed of the first lane, the speed lane, lane number 1, and the second lane. So in scenario 1 and 2, as you would imagine, it would be just regular vehicles on both lanes. But in scenario 3, that would be the AV lane versus a regular lane, because AVs now are exclusive in scenario 3. So Moving on to next slide. Again, for those of you interested in working with a transmodeler, we have used the output for the vehicle to roadside communication sensors from the software. And basically how it works is that you can put several sensors along a roadway, and the software will calculate the speeds, the volumes, the flow, and the densities on each of those sensors or between those sensors. Moving to the next slide, we have the first set of results, which is for the traffic flows. So as you can see on the right side, we have the graphic that shows all the segments that we have collected data for. The segments are indicated by the red numbers, and the cutoff point between the segments are typically the locations where the diverge and merge connections happening. So looking at the graph, looking at the picture on the right and the table, you can kind of see how the trend for the traffic flows are. On the left side of the table, we have results for scenario 2, which is comparing the AV adoption versus the current condition. And on scenario 3, we have the AV adoption plus the exclusive AV lane versus the baseline under each of those market penetration rates as indicated under the AV and AVL letters, the 15, 30, and 45%. And as you can see under scenario 2, we did not see any significant difference between the traffic flows from going from the baseline scenario to AV adoption scenario under any of the market penetration rate. However, under the third scenario where we have an exclusive lane for AVs, there was at some location observed increase in the traffic flows. And as you can see on the table, this number was specifically high during the 45% market penetration rate of the AVs. Moving on to the next slide, we looked at the average density. So the average density had similar results to the traffic flow that we observed. Looking at the scenario 2, so the graph that you see on the center shows the average density along segments 1 to 12 under each of the market penetration rates. The dashed lines are the ones that represent the scenario 3 with the AV exclusive lane. So similar to traffic flow, the average density was not observed to significantly differ from the baseline scenarios. However, on the third scenario with the AV exclusive lane and market penetrations of 15, 30, and 45%, we observed that the density has gone up on some of the segments. And it was expected because when we are talking about AV lanes, they are usually better at maintaining higher speed with lower gaps between them. So there, as you can see on the graph, there was peak observed around 9, 10, and 11, segments 9, 10, and 11, which is just south of the Mira Mesa Boulevard. And it could be attributed to the fact that the road starts to take a curve in that location. And also we have the direct access ramps just before those segments, which add extra volumes to the roadway. Moving to the next slide, we looked at the average speeds. So again, under scenario 2, no measurable differences were observed on average speed comparing to the baseline scenario. Under scenario 3, with the AV exclusive lane, we have some drop in the average speeds. The drop in the speeds were between 2 to 8 miles per hour, depending on the location of the segments that you're looking at. And again, around segments 9, 10, 11, which is just south of the direct access ramps, we have more drop in volumes, which aligns with the increase of the density that we observed in the previous slide. And then the last metric that we looked at was the speed differential. As I mentioned, the speed differential is between lane 1, adjacent to the left shoulder, and the second lane. And in scenario 3, lane 1 is the AV exclusive lane, and lane 2 is a regular lane. Under scenario 2, which is just the adoption of the AVs, there was some minimal change observed in the speed differential between the two lanes, but not significantly. However, on the scenario 3, there was significant speed differential observed between the speed lane, which is the AV exclusive lane, and the adjacent lane to it. So it has been suggested in the previous studies that high speed differential between, for example, HOV lanes and general purpose lanes could warrant installation of barriers between the two lanes. And the thresholds are different. Some suggest 10 miles per hour, some suggest 15 miles per hour. But this is one of the observations that we made in our simulation. And the last slide, just to summarize what we went through in the analysis. So from a corridor capacity standpoint, we observed that including the AV exclusive lane can improve the traffic flows. We observed it for this segment of the I-15 to increase by 15%, depending on the location. Looking at the densities were observed to increase by up to 24%, which again could be attributed to the fact that the AV lanes are better at maintaining lower gaps and more stable flows. From a safety standpoint, our simulation does not reveal any significant flaws and shows some potential benefits as well, because we observed the average speeds to go down from 2 to 8 miles per hour, which can, based on some studies, associated with lower crash severity. So lower speeds could associate with the lower crash severities in suggested in some studies. And at the end, the study that we did reveals importance of understanding the impact of changing roadway characteristics, especially with the last metric, which shows that just by putting AV exclusive lane under a certain market penetration rate, in our case 45%, the speed differentials could go up to 14, 15 miles per hour, which may require some consideration of placement of treatments or barriers. And as Sahar mentioned before, depending on the market penetration rate of the AVs, the number of exclusive AV lanes could change too. So after some point, it could change from 1 AV exclusive lane to 2 AV exclusive lane to eliminate some of these safety effects. And I guess with that, I'll sum up. I will end my presentation here, and I guess I'll have to hand it to Eric from here.
Thank you, Ali. Eric, I think we are ready for you.
Okay, thank you. All right, so now we're going to begin the Q&A part of the session. So I had to jump off a little bit. So if there's anybody who had a question in the chat, please feel free to voice that question. And I also believe that somebody had raised their hand. Was that Sue?
Yeah.
Yeah.
Hey, can you tell me how, on the segment map you had, I'm just wondering how far apart those access points are.
Segment is about 5 miles long, and the access points are I would say are fairly distributed evenly between the segments. So I can't remember exactly how many exit points are between those two segments, but they are usually placed apart
I mean, I
close to
was
1
wondering
mile.
if you could speculate on, you know, if the AVs were not allowed so many access points, because to me that those access points seem pretty close together for a managed lane like that. Usually they're further apart. But I'm wondering if you know, you could envision that the reason an AV wants to use it is that it is a through trip and it really doesn't need to get into the GP lanes. It just wants to get through that section. So, you know, if you shut off some of those egress points, you know, I'm wondering what that would do in your micro simulation. Just, and I know you haven't run the simulation.
Yeah. So we unfortunately we don't have that scenario. But the way that it works is we have some entering and exiting from the transition lanes. So during the simulation, we would observe, sometimes we would observe an AV vehicle getting off of the AV lane and going to one of those exit points, or the opposite, somebody joins in the middle of the freeway to get into the AV lane.
Okay, thanks.
Are there any other questions?
Yeah, I have a question.
Okay.
Hello? Okay. Can you hear me?
Yes.
Yes, we can hear.
Okay. Yes, okay. Okay. My question is, do any of you guys work together with a car company or an AV developer? And what was their response to your research and survey? Can somebody tell me something about this?
Yeah, we did not directly work with any of the AV companies. We actually sent our survey, the expert survey, to some of the manufacturers. Unfortunately, we didn't get that many answers. Maybe a few. I think it's a handful, like 7 or 8, if I remember correctly, as answering to our questionnaire. That we use actually to draw all of those recommendations and that I mentioned, but it was not a direct working with them, no.
Can I ask a question?
Sure, you can.
Good to see you, Sahar.
Good to see you too.
So quick question about the behavior of the automated vehicle in the simulation. Did you guys do any sensitivity analysis to see the impact of changing those parameters on the overall simulation results? I wonder, like, how accurate is the representation of the AV behavior in the simulation itself?
Ali, I'll let you get that one.
Yeah, so our purpose here was mostly looking at the performance of the freeway. The AV simulation, specifically in the transmodeler software, it's not as complicated as, you know, including all the factors into the play, but they have I guess the whole settings for the AV vehicles in the software was set to be mostly focusing on the performance metrics rather than the individual AV vehicles in the simulation. So yeah, and then here we actually talked a lot to the people at Caliper company, which makes this software, to learn about the AV and just make sure that it's a representative of what's out there. And they have used a lot of kind of factors to make it as simple as possible to simulate AV vehicles. But honestly, I think maybe there are some factors that they haven't even included in the software yet, or maybe it's coming in the future.
Thank you. And good to see you, Sue, also.
Thanks.
All right. I think we have another hand raised. You can go ahead and ask your question. Ralph, did you raise your hand?
Yes,
Okay.
You know, that 99% of the cars are actually wider than their usually single occupant. The commuter is actually tall. What I'm saying is you're talking about narrower lanes to increase throughput, but what about dedicated autonomous vehicles that are actually smaller? And they're called narrow track vehicles. Have you ever thought about this? I mean, the whole thing about a new technology is rather than adapting to the present vehicle, the present car. My opinion is to reformat the whole car so that new technology can be easily deployed in the new vehicle, and that would, in my opinion, plea for a so-called narrow track vehicle, especially when commuting. Is that something that has crossed your mind?
That's a very good point. It's actually, there are a lot of unknowns right now, and you're right, everything is actually being developed so fast. So all of the development in the car side, manufacturer side, and also infrastructure side. So there are a lot that could be done. And I think we just touched on a very small part of this big equation. There are a lot of unknowns. Even in our project, I think some of the tasks that I mentioned, we just briefly got some information about each of those. So I still think there are a lot to think about, and those are definitely could be our future work. But we didn't include that in this project. I think, as I said, it was already including a lot of tasks, and we didn't get to some of those in the details that we wanted, and partly because it's a very new topic and there are lots that you need to figure out along the way.
Okay, thank you very much.
Sure.
Thank you, Paul. Thank you everyone for asking questions. Are there any more questions, lingering thoughts or statements? Okay. With that being said, I'd like to thank everyone again for joining the webinar. Definitely like to thank Sahar and Alirad for presenting. This webinar will be uploaded to YouTube, and I will notify everyone via email when it is complete. Our next webinar will be on reference machine vision for ADAS functions, which is set for October 15th at 2 p.m. Eastern Standard Time. Free registration is now open on our safety website in the upcoming webinars tab, along with other webinars. I want to thank